It should. How about you? It's Thursday. Don't worry, you just have to endure it for like one more day. Just get patience. You don't have class on that?
No.
But you have class on Friday.
No, but I'm meetings and work on Friday.
Class like Tuesday, Thursday.
Yeah, but I'm like, sometimes I get like 12 hours.
Oh. I'm always working. Actually, that one was yesterday. Got here at 11 and I go home till 11. Yeah,
Hello.
whatever. I feel like everyone shows up late for this class.
Later and later,
They show up.
they do show up.
It's always.
That clock is also ahead.
Oh, okay.
Hello.
Wait, can I ask you what made you go into this field? Like,
Yes, you may ask me that.
What was it, like a little event?
Well, I mean, part of it's very stereotypical. I liked space when I was a little kid. You know, when I was in kindergarten is when Voyager passed by Uranus and Neptune. I think kindergarten was maybe Uranus and Neptune was like in grade school or something like that. So all these pictures of like these new, you know, these worlds that we've known but never had pictures of came out around that time. It was very awe-inspiring. But when I was here at UCSD, I worked with Sally Rye on a space project, and I worked with another professor on an astronomy project. And I wanted to go into grad school for astrophysics so I could become an astronaut. It turned out I was much better at being an astrophysicist than being an astronaut.
Really? Why?
Well, I mean, this is around 2000, and the astronaut program was starting to kind of shrink down quite a bit with the space shuttle sort of projected to start to wind down, and it's a tough process to become an astronaut.
Really?
Yeah, I mean, you know, there are literally tens of thousands of people who apply when they have calls, which are not that often, and they might take a class of 10 or 20 or something like that. So many people will apply until they're about 40 or 45 years old, and then kind of give up at that point. So, yeah, this was just turned out to be a better job.
And why are you sitting like brown? Wait, is it brown?
Brown dwarfs, yeah. Well, partly that's what I worked on as a grad student, and at that time there weren't really any of those known. So part of my work was to actually discover the first ones, it's very common to continue to work on something that you worked on as part of your thesis because you kind of become an expert at it. But there's other stuff I'm interested in as well. Okay, so let's get started. Just a few important announcements, particularly relevant to the project before we start. Again, if you have listed on your grade sheet something that says needs revision, you have to see me today, and I still need to read over yours. So
I was going to come to office hours anyway.
that would be great. Okay, may not be necessary, but it's okay. All right. So either see me after class or see me in office hours today, but you definitely need to see me because in order to really proceed with this project, we have to sort of address a few issues. And it's many of you, so don't feel like you're being singled out in any way. And thank you to those you've already talked to. So those I talked to can go ahead and proceed. But if you haven't talked to me yet, please do so. The project paper is due next Friday. I'm adding them, so it's turned into TED. The Turnitin assignment is posted there. I also want a hard copy because it's just easier for me to grade the hard copies. So please turn in the hard copy to me in the box, the same usual place that it's located. So one thing I'm adding here is up to this point, I just had turn in paper and it'll be graded. I'm a full believer of the editing process, and so I will give you a chance to re-edit your paper with my comments. I'll get all those papers back to you by the end of week 10. And you have the opportunity, you don't have to, but you have the opportunity that if you want to re-edit your paper based on those comments, you can get up to half of the points you've missed. So that means, for example, if you got a 50% on the paper and you make all the corrections I asked for and it's a beautiful paper as a result, then you can get up to half those points back so you get maximum 75. Does that math seem clear? Okay. So, if you get a 90 on your paper, it may not be worth your time to get up to a 95. If you get a 20, it probably is worth your time to send it and edit. And this also means it's really critical to make sure that first paper is done as well as possible because it's only half the credit back in return. So, don't think of this as a free pass to just send in, passing junk on Friday, next Friday. Make sure you do your work and edit that paper as well. But I do want to give you an opportunity to sort of re-edit that paper to refine it. The other thing I'll remind you is that the rubrics that I'm using to grade the paper and your presentation are online on TED. So please look at those because those are the things that I will be using to evaluate, and you should be hitting those metrics in order to get a high grade. So that's the cheat sheet for your project. All right, so that's new, and that'll be up on the project information page. The other thing is on the presentations. I had originally posted that you have to send me your presentation slides by next Thursday. I'm going to move that up to the following Monday. So the papers are due on next Friday. Presentation slides, if you're doing a presentation slide, need to be to me by email by the following Monday at 4 p.m. So kind of like you're doing your news reports, right? Make sure you turn in your slides the day before those presentations happen, okay? So you have it up until that day. And that includes those presentation slides, or if you're doing a creative project and you have a product you're trying to make, like some kind of model or some kind of simulation or some kind of poem or something like that, those also have to be turned in by the following Monday. So you have a little bit of time after the write-up to polish those projects as well. All right, any questions on that? Okay, so just keep in mind that the presentations and all the presentations are going to be happening during lecture in week 10. I'm going to be assigning your times. So, if you have any specific requests, please let me know, but I will probably just randomly assign them. Part of your participation grade for the class is providing feedback for the presentations during that week. So if you're scheduled for Tuesday, and please show up for Thursday as well, because, that's part of your participation in the course is to help each other in improving their projects, okay? All right, any questions on project stuff? Yes, ma'am.
My thing is like food related, so what I just
Is it-
like show you like a picture of like what it is, because I'm gonna make it twice, just like the one time to test if it actually works, and the second time to actually present it. So I'm gonna just show you like a picture of like.
You mean for like this Monday?
Yeah.
Yes, show me a picture, but of course bring in the food product for your presentation. Yeah, that would be fun. Any other questions? Okay, if you have them, please let me know. The last announcement note is make sure you're checking your assignments on TED. I do consider, there are things that are missing that are sort of things that you feel like there was a question that was wrong. I think, for example, in the midterm, there was a question that, there was a sort of confusing equivalent question on the practice midterm. And so I can understand why everyone got that wrong. So I just corrected that. But someone's got to tell me about that. All right. So please look over your assignments. If there's anything missing, please let me know immediately. I won't take any requests for regrades or reassignments or anything like that after week 10. All right. So you have up until then to let me know about things that are missing. It's your responsibility. All right. So make sure you check. Any questions? Okay. All right. So today we're going to hear our last two news reports from Jacqueline Nguyen on a strange exoplanet discovery and Michael Shee on dinosaur-killing asteroid hit. So, Jacqueline, you want to come on up? Oh, and please pass around sheets. Okay.
So my project was on a discovery from researchers at the Australian National University of a planet orbiting a star 500 light years away from here. And
Yeah.
oh yeah, this is an artistic impression of what it's supposed to look like that I took from the article too.
Sorry, there's a technical problem with your next slide. Oh, does that look right? No, it doesn't look right at all.
So I guess I can start telling you about this planet. So the star is an M-dwarf star, and so it's dim and it's cool, and it's 1/20th of the brightness of the sun. And the planet is orbiting closely to the star, and it was discovered as, I think it was observed as a transit in front of the star, because there were small Revote telescopes. I think they said it was from the ANU Sighting Springs Observatory. And they discovered the small shift in the brightness of the sun, and that's how they determined that there was a planet orbiting the sun. I mean, not the sun, the star, sorry. And they also confirmed this fact by using the Magellan telescope, which is in Chile, which is one of the world's largest telescopes. And for some reason, they also used some amateur astronomer who works in his backyard, to confirm this. So I guess some of the observations that they made is that the planet orbits the sun every 3.3 days, and that's 1/10 of, I think it's the orbit of Mercury. It has a mass similar to Saturn, and its size is similar to Jupiter. And they want to detect the composition of the atmosphere in further experiments. And I mean, I guess I'm kind of exaggerating my conclusion, but they had a lot of big questions from this discovery. And one of them was how the planet might have migrated into the inner orbit system, because they believe that it had formed in the outer solar system, and it somehow migrated closer towards the sun. And they also, their second question is how, I guess how this planet might have formed, because most of the stars that we've discovered so far have Jovian-sized planets, and that they tend to be hot. And this one is cool, they're assuming, because the star is so dim. So they're saying that just raises questions about our theories about how planets evolve.
Okay. 2 questions. Yes, sir.
Yeah, so did the amateur astronomer discover it first, and then they confirmed it?
No, their telescopes at the observatory observed it, and they confirmed this by using the amateur astrologists.
So they used him.
What?
They used him like he was just like.
Yeah, I guess it's just like some
Probably willingly.
useful boosters.
Skylar.
So I don't know if you already talked about this or not, but where is this in perspective to where we are?
It's 500 light years away from here.
Okay, any other questions? Okay, we're going to hear more about transient planets a little bit later in the class, so thank you for introducing it.
Okay.
Thank you. All right, so again, please provide some feedback for Jacqueline on her presentation. Let's see if I can get this back again. Okay, Michael.
So about 66 million years ago, an asteroid hit off the coast of Mexico, and that triggered the KT mass extinction. So that's what's known. And now the researchers think that this asteroid also caused a massive volcanic eruptions all the way off in India. That is today known as the Deccan Traps. Yeah. And they think that this massive eruptions that the meteor caused sometime later contributed to the KT mass extinction. And some coincidences of note is that the last 4 mass extinctions out of 6 have occurred at the same time as these massive eruptions similar to the Deccan Traps. So the theory that they came up with is that the meteor caused existing volcanic systems. It motivates the magma in the existing volcanic systems, and it speeds up their rise. So what should occur in regular intervals of longer period, because of the meteor, it speeds up their ascent. So once the meteor hits, they think that it'll take about 100,000 years for the magma to rise and create the Deccan Trap. That's exactly what we see in the real world. So the researchers note that it's extremely unlikely for the Deccan Trap to happen just coincidentally, right 100,000 years after the meteor impact. Yeah, and the regular interval is that they rise every 20 to 30 billion years. So that's like a long interval. That's basically it.
Okay. Any questions? Okay, 1, 2.
Okay, so why do they rise every 20 or 30 million years?
That's like the regular process. Like
Why?
I don't know. It didn't go. It's like a natural. Like they're supposed to rise in regular intervals of 20 to 30 years. These massive eruptions.
Yeah, gotcha.
So is this like the time when it erupted regularly?
What?
Is this like the time when it erupted regularly? Like the
Yeah.
Okay. So even though it's like 10 or 100,000 years, they think it's directly correlated.
They think it's unlikely, and it's also this isn't the only case. There's a lot of like he notes that over the past 6 mass extinctions, they could find 4 massive eruptions that coincide with 4 of the respective impacts.
Do these usually like occur like? I mean, I don't know if there's like other asteroids that like happened before, but with these spoonheads, any others like occurred like throughout like large gap of time between like some sort of kind of erupting event rising the.
Yeah, it It has to be like a big asteroid. Yeah. Like they also found that like earthquakes of magnitude 9 or above can cause this sort of Deccan Trap we see, and that's like a huge number. So they also, and that's consistent with how much earthquake the impact would have caused.
So, and maybe Sebastian, related to your question, this is they looked at how these eruptions correspond with mass extinction. So they also look at just asteroid impacts that may not have led to mass extinctions. Did they have any discussion about that at all in the article?
Not that much.
Okay. So they just related to mass extinctions.
Yeah.
Okay. Any other questions?
And the volcanoes exhume like noxious plume that contributes to the mass extinction. They think.
Is that the main like
They don't,
cause of death?
they don't know. They just think it contributes. Like that's all they're saying. They're
Okay.
willing to say. Basically.
Sebastian?
Did they say why it takes so long for like from the point of impact for the to
Well, 100,000 years is not long in the volcanic
Yeah.
cycle. It's actually surprisingly fast. That's why they're
Skylar?
And I don't know if this is already covered, but in the span of 100,000 years, does that mean like it would happen sporadically throughout the 100,000 years, or just like 100,000 years?
Just 100 years.
Everything's
100,000 years after the it takes that long for the plume heads to rise up to the surface.
so like, do they all do it at once, or is it sporadic? Like after that, was it?
Like once like at the 100,000 years mark, it appears.
Maybe, I mean, is there like a time scale over which the eruptions occur? Like, does it take 100,000 years, and then are there eruptions for
Oh,
10 minutes
Yeah,
or
so,
100,000
Yeah,
years?
like is it just they all go off at once,
Yeah.
or
Did they talk about that at all?
No, I don't think so.
Okay.
Yeah. I think it appears and then it erupts for a while. Like it has to. I don't know. Not sure.
We don't know what while means in
Yeah.
geological terms.
Yeah.
Okay. Okay. Questions? Yes, ma'am.
How big were the plume heads?
They were massive. Like
Did they kill them?
they don't know if they killed everything, but they definitely know it contributed to it.
Well, we know they didn't kill everything
Yeah.
because we're here.
It's quite remarkable. It's like it hits in Mexico and then the plume heads rise in India.
I mean, one piece of information that's important is that a related eruption that happened about 100,000 years ago was the Toba eruption that centered in the Philippines, and that buried India in 9 foot of volcanic ash, and you can see that in the geological record. So, and that's not one of these. This is actually bigger than that. So certainly, and regionally, it would have probably done a lot of damage because it buries huge, areas of land in volcanic ash and magma. Whether that has a global effect may have more to do with the sulfur dioxide and other emissions from the volcanoes. It's bad locally and globally, but for maybe different reasons. Okay, any other questions? Okay, thank you, Michael. Again, please provide some feedback for Michael's presentation. Great shuffling. Awesome. Okay, so today we're going to continue on with our detection methods, and thank you, Jacqueline, for talking about transit objects. We're going to talk a little bit more about transit technique today, and we're going to talk about how we use these techniques not just to find the exoplanets, but also to say something about them, characterize them in some way. Our planets in our solar system are actually relatively easy to characterize because we can resolve them. We can take pictures of their surfaces or their atmospheres. We can send probes to them. But that's not something we can do for planets around other stars. And so there's all sorts of techniques that have been developed to actually learn something about the physical nature of these planets and how they orbit. And so I'll talk about that and then talk about what we know about planets, exoplanets in general, because that's, of course, relevant to looking for places that might harbor life, is knowing what the planet's actually like. Now, just as a reminder, we have these two areas of techniques of finding planets: direct techniques, where you actually look for the planet, and that requires getting around the issue of contrast and resolution. Contrast because the planets are typically up to a billionth in brightness compared to the star, right? And particularly if we're looking at the visible band. And so it's very hard to see that firefly next to that spotlight. And particularly also resolution if it's right next to the spotlight, which in sort of astronomical terms it is. You know, we've talked about the sort of scale of these things are less than an arc second away from the stars. From our perspective, even the biggest telescopes have a hard time resolving the planet from the star in those cases. So we have different techniques for getting around both of those problems. One looking at the infrared where that contrast is lower, and then also using coronagraphy to block out the light of the star as much as we can. And then the other way is using indirect techniques where we don't actually see the planet itself, but we see what the planet's effect on the star is. And so we talked a lot about radial velocity techniques as a way of seeing how the star gets moved by the planet orbiting around it using Newton's third law. We'll talk about transit as another sort of indirect technique today. Now, all of these methods of finding planets have their particular biases, their particular selecting effects. Good. All right. When we talk about direct detection, of course, we're looking for the light from the planet, which means the planet better have a lot of light coming off of it. And in fact, most of the time we're doing this again in the infrared, we're mostly looking at the black body thermal emission from the planets. And that means these planets have to be pretty warm. And so one of the biases for these detections that we talked about on Tuesday is that these are mostly young planets, very massive planets, and they still have a lot of their initial formation heat, right? They haven't radiated away yet. So these are particularly biased towards looking for planets around young systems, right? And they're also very massive systems, so these may not be the greatest places to look for planets that might harbor life, right? It's still too early in their evolution, and they're much, much more massive than the kind of planets that, terrestrial type planets that we know life has here, at least on Earth. In terms of gravitational effects, right, this is again how the planet pulls on a star, and it induces this radial velocity variation. This is the radial velocity curve for the planet 51 Pegasus. And you can notice that, as we talked about, the period of this planet is very, very short, around 4.2 days, which means it's a very, very closely separated planet. Now, who has their voting cards with them? If you don't, there's a couple in the back. I got one here. So, all right, just as a way to sort of remind ourselves about some of this information, we'll do a couple questions here. All right, so here's the first question. Suppose you kind of start with the same mass as the sun, moving back and forth for a period of 16 months. What would you conclude? Think about this to yourself. Okay, everyone got their answer? Count of three. 1, 2, 3. That means flip your card. More dramatically than I'm not sure this is the right answer. Okay, there's a little variation, and actually as I stand here, the variation isn't continuing, which is interesting. Most of you have at least one neighbor near you has a different answer. Find that neighbor and convince them that you are correct based on what you know about radial velocity planets. 30 seconds, go.
Okay, so
3 steps up was a period of 16 months. And we're talking about Revote, which is the most so 16 months is really 12 months. So if we had like a sized planet in Earth's orbit, then the radial star would be 12 months. It would go back and forth for a long period. So if it takes 16 months, it means the planet that's orbiting the star has an orbit of 16 months. I assume.
Okay, let's do a quick revote. Count of 3. Is that your answer? 1, 2, 3. Oh, that was pretty dramatic. Wait, I don't. You're folding your paper in your lap. Go for it. Go for it. Okay. Oh, by the way, if you're undecided, that's the back side of the paper, which is E. And I don't know. That is a perfectly valid choice.
That happens.
That happens. Wow, look at all the lights come up. All right. If you can wipe it, the rest of you have basically the same answer, which is what? If I say that most of you have basically the same answer, you could probably be more confident then. E is not the correct answer. E is the I don't know answer. Those of you who picked an answer, what did most of you pick?
B.
Oh, come on. Most of you picked be confident. Yes, it's B. All right. So B is the best answer for this question. Why? Yes.
Because one radial period is like the planet going around the sun. So the radial period is 16 months. The orbit is 16 months. It means longer. It means their orbit's farther away than the Earth.
Right. So the Earth's orbit is 12 months, right? If you have something that's orbiting at a longer time scale, Kepler's law says it's got to be at a different distance. If it's around the sun, and that's actually why this part of the question, the same mass of the sun, is an important one. If I said that this was a planet orbiting around the sun and we didn't know what type of sun it was, what would be the answer in that case? Yeah, D. We don't know because it depends on the mass of the star. So that's actually an important part of this whole process of figuring out what kind of planets these are. Okay, second question. Maybe need more time? Okay, count of 3. 1, 2, 3. All right. Seems to be quite a lot of consensus around one answer, which is what?
A.
Now, a whole bunch of you have a different answer, which is what? Yeah. About a quarter of you have the answer D. So normally when you have like most of the folks in class have one answer, I usually go with it. But a quarter of you have the answer D. So it's one of those two. Can someone argue why it has to be A? Since the majority voted for that, there should be plenty of volunteers. Yes, Sebastian?
Well, because the amplitude is smaller, then we can conclude that the planet has less of a gravitational pull on the sun, and so therefore it must be smaller, or at least less massive.
Okay. All right. Any other comments from the A's on that? How about our handful of D's? Yes, sir. Okay, could be further away.
So the gravitational forces, or since it's farther away, its force of gravity on the sun is less.
Okay. All right. Any other D comments? Any A responses to that? Sebastian, as the
Changed my mind.
oh boy, okay, you're not a very good flag bearer for A, traitor. Anyone who still believes in A want to respond to that comment? What you want to do a revote? Okay, let's do it. Yeah, Sebastian, go ahead.
Is the period the same as Jupiter's? Doesn't say that.
No.
Okay.
All right, count of three. 1, 2, 3. Thank you for your honesty. Boy, you're so easily swayed. Everyone now voted. Everyone now voted.
D.
Yeah, okay. Everyone now voted.
D.
Yeah, you should be confident when I say everyone. You're not going to be isolated, right? Except a couple of you still held on to A, which is fine. So the period is not specified here. So that's a piece of information we're missing. And certainly if the planet is further away, it might be a smaller amplitude. But what if I change this and say it was the same period as Jupiter? I'm going to play with you a little bit. All right, so I'm changing the question to say it has the same period as Jupiter, but a smaller amplitude. What would you vote? Count of 3. 1, 2, 3.
A.
Boy, quietly. wait till I say. Everyone say.
Oh, sorry.
So easily swayed. Everyone said.
A.
That's still wrong. There's one other piece of information you need to know to connect amplitude to the mass of a planet. And it's based on the stuff we did in lab yesterday.
Orientation of the observer.
Explain.
So if you're looking at it, say from on top, there won't be any amplitude change. If you're looking from the side, that's like the maximum.
That's exactly right. So not only do you have to worry about the period of the planet, you also have to worry about the tilt, right? When we're measuring air velocity, we're looking at the motion of the object in our line of sight, the motion of the star in our line of sight. If the star system is tilted to its face on, how much velocity change will we get from the star, from the orbit of the planet in that configuration? 0, right? 0 amplitude, which means there's no planet there, right? Wrong, right? Orientation matters. So not just the period, which affects how far away the planet is and how much of pull it is, but also the orientation. Both of those effects have to be in place. So the rate velocity technique is a little bit tricky because you have to take into consideration the geometry of the system you're looking at. So whenever we make measurements of the planets in this rate velocity technique, the only thing we know is a minimum mass from the star, right? It can be greater, but we're not seeing the full pull because we're only seeing the direction in and out of the sky, right? So that's something to always keep in mind. The amplitude is something that gives a rough idea of the mass, but it only gives us a lower limit. We actually have to know the orientation of the system as well to figure it out. Okay, so just to review this, so we have these selection effects for radial velocity planets just as we do for direct imaging. Right? They generally have to be very close to have that sort of strong gravitational pull. They have to be fairly massive planets. They tend to be detected around bright nearby stars because it's the only way we can get the very high resolution spectra. And what I don't have here is that you also don't actually exactly know the mass, right? You get a limit on the mass. And that's really going to favor the most massive planets because if you're already damping down the effect by orientation, you've got to have an even bigger planet to sort of compensate for that. So this is really skewed to really massive planets. And most of the massive Jupiter planets, sometimes up to 20 times the mass of Jupiter, have been found in this way. But it's very hard to find small planets because not only do they pull less, but the orientation of the system might be so that they even pull in the direction that we're looking at less. Okay? So those are important things to keep in mind. So again, these are all selection biases, and generally they don't help us find the kind of Earth-like worlds that we're interested in if we want to actually find life. Now, I started introducing this concept of transits at the end of class on Tuesday. This video isn't working, but this is now a working video of the stereo satellite that's been staring at the sun in sort of 2 different directions, actually catching Venus passing in front of the moon. And this is a really large transit, in part because Venus is much closer to us than these planetary systems are, so it has a relatively larger scale. But of course, as it passes through, it's blocking some of that light from the sun. And we can measure that dip in the light by just making very accurate measurements of the brightness of the star. As the planet passes in front, it will decrease it just by the area, the surface, the sort of projected area of the planet in front of the star. That will decrease the light until it passes in front and out. And this kind of characteristic shape is the kind of thing that people looking for exoplanets through the transit detection method are looking for. Yes, ma'am.
I remember reading in the book one time that they also measure, like if something's there by the brightness, if it gets brighter. Is that if the planet passes behind the star?
We'll actually talk about that a little bit. And in fact, when the planet passes behind the star, the total light from both objects goes down a little bit, right? Because the planet is also reflecting some light back. And we'll talk about that secondary transit in just a little bit. Now, the brightening effect is that microlensing that I talked really briefly at the end. That's the gravitational lensing. Did I talk about that on Tuesday? Okay. So you can have a planet that acts as a lens. The mass of the planet acts as a lens from a distant background star, and that will cause it bright. So it is still passing in front of the star, but it's not actually not blocking the star. It's actually magnifying the light from the star that's really far away. This is only happening for the planet and its host star. Right? The other is it's magnifying light from a star that's very, very far behind it, unassociated with the planet. So yeah, there can be magnification events as well. So this is the kind of the characteristic shape we look for. This is some actual real data that shows exactly that shape in sort of 5 different planets that were found early by the Kepler system. And you can see some of the orbit periods here. They're, again, very short, just a matter of days, right? These are the same kind of planets as 51 Pegasus, very close planets to their stars. The only difference is that some of them are actually quite small. This planet right here is a very, very small planet. And the amount of dip, so the dip in the brightness here depends on the ratio of the area of the planet to the area of the star. So anytime you see a big dip, you know you're seeing something really big pass in front of the star. Anytime you see a little dip, you know you're seeing something that's very small. And that's sort of equation here. All right, let's try another little vote to test this. This is, again, review. And those in the back who can't see the hint, Jupiter is about 1/10 the radius of the sun. Okay, count of 3, 1, 2, 3. You flip the thing around. Unfold it, yeah, and there you go. That's E. Okay, pretty good range of answers. So go ahead and find someone next to you who has a different answer than yourself. You may have to look around a little bit and convince them mathematically that you are correct, as opposed to the, I don't know. It's not actually mathematical. This is the part where you talk to each other.
Very so.
Okay, let's do a revote.
You have more than very.
Count of 3. 1, 2, 3. I see a lot more E's than last time. I see a whole row of E's up here in the front. All right, so what's confusing about this problem? For those of you who are E's. What's that? Oh, there is. Oh, sorry. You're choosing E because it's one of the answers. Sorry.
Yeah.
Sorry. Okay. So, okay. Put up your votes again now that I remember what E is. All right. There is absolutely no consensus on this answer whatsoever. So let's work this out mathematically. The depth of this change in brightness here is the ratio of the areas, right? It's how big of a black spot that goes in front of the bright spot, which is the star. If you have a radius for an object, what is the area of that object if it's circular? Pi r squared, all right? That's elementary school geometry, right? Radius, area of a circle is pi r squared. So when you have the radius of two things and you want to get the ratio of the areas, you're just taking those radius and you're squaring them. Right? The area of a planet is pi r squared of the planet. The area of the star is pi r squared of the star. So we're looking at the ratio of the radii. Now, I gave this hint that Jupiter is about 1/10 the radius of the sun. So what is the ratio of radius of planet over radius of sun? What is the ratio of radius of a planet over radius of a sun squared?
1 over 100.
1 over 100. What is 1 over 100 in percentage numbers? 1%. 1%. So if you're down at 0.01%, too small, maybe you forgot to get rid of the percent sign. Okay, but percent means per cent, per 100. Right? So this is 1 per 100. 100% would be blocking the entire light of the star entirely, which happens, by the way. Right? We have these other objects called white dwarfs that are very bright but very small, and a Jupiter passes in front of that, completely blocks the light of the white dwarf entirely. We haven't seen that yet, but I bet you that's out there somewhere. All right, so this is the calculation, right? It's the ratio of the radii. That's about the spot size. All right, let's test this knowledge again. What if the Earth passes in front of the sun? And here's the hint. The Earth radius is 1/100th that of the sun, roughly. Do yourself first. Do yourself first. Don't show me yet. Don't show your hand yet. First rule of gambling. Okay, count of 3. 1, 2, 3. Okay, most of you are answering the same answer, which is what? E. All right. 1/10,000. 1/100th times 1/100. 1/10,000. And that's 0.01%, which is 1/100th of that, of course. Okay? So these are the kind of signals, if you're looking for an Earth around a star, this is how big of a dip you're looking for. 0.01%. 1/10,000th of the brightness. That is a really high fidelity measurement. All right. Most of the time, if I'm doing photometry of a star, I'm very happy if I can get down to like 1%, this kind of photometry. So to do this, you really need to have a very special instrument. That's one issue. The other issue is that we still have a sort of angle problem, resolution problem, because in order for the planet to pass in front of the star, it has to be exactly in line with the star. Now, in the radial velocity technique, that helped us see a signal. But if it was tilted a little bit, you could still see some radial velocity motion. It might be damped a little bit, but you still see some motion in the direction. Transit's required to be somewhere actually on the disk of the star. So you can calculate the angle in which that would happen, the angle that you have to see the system by, in which that can happen. And that's just simple trigonometry. The largest angle is a triangle where this is one side of the triangle, and the distance that the planet is from the star is the other side of the triangle, right? And the size of that angle is the range over which you can actually see this transit. And that angle is going to be pretty small because usually the radii of stars, right, which are usually some very tiny fraction of an astronomical unit, about 0.5% in the case of the sun, is often much smaller than the actual orbit size of the planet itself, which might be on the order of an astronomical unit. Right? Now remember, when you calculate angles by this ratio, those angles are in radians, right? So you have to convert that to a degree if you want to actually get the degree measure. But let's say, take an example, the sun is about 0.005 astronomical units. You can just you can calculate that. The sun is about, or the Earth is about 1 AU from the sun. So that translates into about 0.005 radians. That's the ratio of 0.005 to 1. And that translates into an angle that's less than about 1/10 of a degree. So in order to see, the Earth passing and transiting from the sun, you have to catch that system to be exactly edge on to within 0.1 degrees. That's a pretty small tolerance. What's the outcome of that? You have to have this very narrow range of angles to catch these transits. What does that mean in terms of searching for them? So two effects. One, it's as the planet moves further away, it gets more and more unlikely, right? This number gets bigger and bigger, and this number doesn't change. It's the radius of the star. So you get more and more unlikely to find planets as they get further and further away from their stars. What does this mean more generally in just looking for planets by this technique? So that's the same argument. But I'm thinking I want to find all the planets in the galaxy. Am I going to do that doing this? Why not? Yeah.
Are you just not aligned to see planets? Because you, as an observer, you have to be aligned at the right level.
At exactly the right level. Yeah. Do we have control of the alignment of other planetary systems? Not yet. Okay, not yet. Maybe someday. All right, but no, we don't have it, and probably so. If the angle at which you can see this is say 0.1%, that means out of the 1,000 planetary systems that are have planets at an Earth radius away from them, we're only going to see one out of those 1,000. Right. So this severely underestimates the number of planets that are out in the galaxy. And it also means that in order to find any of these, you have to look at literally thousands to hundreds of thousands of stars, because you're only going to get one out of every one of those 1,000. So the surveys that do this, and Jacqueline mentioned one of those today, that sort of HAT-P survey, requires looking at very dense star fields, right? In particular, looking at in the plane of the galaxy where there's lots of stars, looking at the bulge of our galaxy where there's lots of stars, looking at other sort of dense star clusters like globular clusters. These are the really only places that you can find these transiting planets. If we want to find them around sort of stars near the sun, we've only got, again, like a 0.1% chance of doing it, even if we have the right technology to do it. So lots of star fields is also part of it. And then it's also, you have to have lots and lots of time on stars, because those planets only take a small bit of time to actually pass from the stars. Those transits might be only, an hour long, compared to the 1-year orbit that it takes. So it's a matter of lots of stars and monitoring those stars. So having amateur astronomers, and amateur is in quotes because sometimes the astronomers have bigger telescopes than we have, right? They're rich, so they can buy these things off the shelf. But also looking in areas of sky, or large areas of sky where you've got lots and lots and lots of stars. Both of these things need to be done in actually order to find these transits. So even if we have the ability to make these accurate measurements, these things are still sort of piling against this technique. Nevertheless, we've talked about this particular mission, the Kepler mission, which over the last 6 years has been monitoring the sky. And look at how many stars it's been looking at. 150,000 stars is sort of the sample it's using to find planets. If it's 1 out of 1,000, that means you should find 150 planets, right? That's how you sort of game the numbers, right? Look at as many stars as you can. Now, it turns out that Kepler has found a lot more planets than that, because there are actually a lot of planets that are very close to their stars. This is a sort of visual compilation of all of the planets that Kepler has found, either candidates where they're still following them up to confirm their planets. But about 1,000 of them have been found with this mission. That's a huge number of planets. In fact, that's about 3/4 of all the exoplanets that we know today have been found by the Kepler mission. Sorry, 2/3. It's getting up to 3/4 now. And all sorts of different stars. Big stars with big planets around them. Small, tiny stars down here that have small planets around them. All right, you can find a fairly wide range of planets when you look at all different types of stars. This is a fun little animation that one of the folks at Kepler has put together. This is just showing the sort of range of orbits of the type of planets that Kepler has found. The bigger dots are bigger planets. The little dots are littler planets. Some of these sort of orbits are closer to the sun. I think that's why they're in red. You can just kind of trip out on this for a while. Actually, it gets even better because it starts to zoom in. Let's zoom up to that. This gets really fun. Ooh. Look at some of these systems. 6, 7 star planets found around one star. Right? That's 6 or 7 transits found around these one stars. And as, of course, as you get closer and closer, these things are spinning around really, really fast. Very, very short period planets. It kind of messes with you after a while. Okay, I'll stop that before y'all fall asleep. So this mission has found an incredible diversity of planets because this technique actually can find a very different type of planet than the radial velocity method. And one of the things it can do is find multiple planet systems. And so this is the transit light curve data. Okay, you can see the scales on this, right? This is 1 normalized, and it goes down to 0.099, like 6 or 7. Right, that's a 0.03% transit. Right, that's a small planet, but it's got all sorts of different sizes of planets here, depending on their dips. And this is kind of a picture of what that planetary system might look like based on the timing, the periods. So you can measure the distance from the periods, and also the sizes of the planets, which you can measure by how deep these transits are. Right. Here's another interesting system. There's also planets that are orbiting around multiple star systems. So this is the light curve from this particular planet, and the light curve is here, and it's a little bit sort of up and down because the star itself has some intrinsic variability, but you see these dips that happen in sort of odd places. And what they've been able to figure out is that, in fact, some of these dips are coming from this planet transiting the primary star, and some of these dips are coming from the planet transiting the other star, and you have this sort of unusual sort of beat pattern between these different things. And they can, again, based on sort of the properties of these transits, infer a whole bunch about the system, right? So this is a planet that's going around literally 2 different stars. By the way, planet going around 2 different stars. Remember that from Star Wars, right? That was a big news when this happened because, you know, people thought, well, maybe you have planets around 2 other stars. And most people thought, no, there's no way. It's too unstable. There's one right there. All right? So now we know you can have planets around multiple star systems, which is important because a lot of stars are in multiple star systems. This technique has been able to find very unusual planets, particularly a class of planets that we now call super Earths. So here's the size of the Earth. This is the size of Neptune. Neptune's about 3 or 4 times as big as the Earth. And now we know that there are planets that have sizes that are kind of intermediate between that range. Right? So things that might be terrestrial, might be kind of icy gases. We're not quite sure what the composition is yet. But they're planets that we don't have in our solar system. Right? In our solar system, we have these little rocky planets and big gas planets. There appear to be a class of planets that are intermediate between there, and we're starting to find these from this transit technique that we didn't know about before. This technique is also, particularly when it looks around small stars, right? Remember, what matters is the ratio of the planet area to star area. So if you want to find small planets, you can look around small stars. And in fact, Kepler is now finding planets that are smaller than the Earth, right? Even smaller than Mercury. Here's a planet called Kepler 37b, which is actually smaller than Mercury, right? And it's, again, found around a small star because that will produce a strong enough transit signal. But, you know, these are planets that otherwise we would not have been found from the radial velocity technique because they're just so low mass that they don't pull on the star enough. So that's a new sort of type of system. The transit technique, because this mission has been up for 6 years, has been able to monitor these stars long enough to catch planets that might be in the sort of same distance as the Earth is from the sun. And so it's starting to find planets in what we call the habitable zone. We talked about this a little bit earlier in the quarter. This region around a star in which you could have liquid water on the surface if you have a surface. Doesn't guarantee there's liquid water there, but at least the temperature conditions are right. And we've already started to find planets like this super Earth that's in the right zone, up here, in the right zone around its star, that it could potentially have water on its surface, or maybe its moons have water on its surface. Right? I should say one of the greatest, most recent and very exciting examples is this planet called Kepler 185f, right, 186f. This is a 186 planetary system found by Kepler, and F means it's like the 5th planet that's been found in the system. So this is one of these multi-planet systems. And what's exciting about this is the size of the transit indicates that this is an Earth-sized planet. Might be an Earth mass planet, we're not quite sure. But it's at least the right size to be a terrestrial world, and it's in the habitable zone. So we might be looking at potentially the first world in which, might be an analog to Earth. Now keep in mind, we've got 2 other planets that at one time or another have been in the habitable zone of our sun, which are what?
Venus and Mars.
Yeah, Venus and Mars. Are they currently habitable? No. Okay, so just being in the right place does not necessarily mean the right conditions. Okay? But this is at least a start. And I'll just mention that, so the discoverer of this is Alyssa Quintana. She was actually a colleague of mine when I was an undergraduate here. So this is, this could be you in 20 years, finding habitable worlds. Cool. All right. So all sorts of great things are coming out of this, and I know some of you are doing these in your projects, so we'll hear more about this in week 10. But what kind of planets is Kepler finding? Right? They're finding, just like rate of velocity, they're finding planets close to their stars. That's because it has to be just aligned just the right way, and the alignment depends on that sort of ratio of size of star to distance from star. So this is favored towards finding planets that are close to their stars. In our solar system, most of the planets are aligned in the same plane. So once you see one planet transiting a star, chances are you're going to see a few more. And that's indeed what's happened for these Kepler missions. And so we find lots of multi-planet systems from this technique. We find all different sizes because we're looking around all different types of stars. So we see big planets around big stars and small planets around small stars. And that means we're actually accessing this sort of terrestrial planetary zone by looking at these very small stars. So these selection biases is trying to be a really great way to find habitable zone worlds. And as I just showed, there's a couple examples of them that we now know. Something like 8 or 9 planets found by Kepler now appear to be habitable zone worlds. So this is actually a very exciting time. Keep in mind, this happened just last year, right? We're in a very exciting time for this sort of discovery of worlds that potentially could harbor life or could potentially places that we go. Okay, now I'm going to move away a little bit from the detection and talk a little bit about what else we can learn from these transits. As I mentioned, as these planets go around, they block out a certain amount of light so you can measure the size of the planet. But there's also other things you can measure as it's passing around, right? You can measure the light that's passing through the atmosphere. We'll talk about that in a little bit. And we can see the light that's reflected from the planet as it goes behind. And we can even see the thermal emission from the planet as it goes behind, as it's blocked by the sun itself. So let's talk about the size thing again. In fact, you can combine both the transits that we can measure from the brightness curves and the radial velocities, and that's very commonly done. One of the great things about having a transiting planet is that there's no ambiguity about where its inclination is anymore, because it lined up with the star. We know exactly what its inclination is. So we get exactly the mass of the planet, and we get the size of the planet. Now, in the past, we've talked about why it's important to have mass and size. What does that tell us ultimately when we combine those numbers? Density. Why is density, why do we care about density?
Determine the composition of the planet.
Yeah, so that tells us something that's actually important to the actual composition of what this thing is, what this planet actually is. So there's been a whole bunch of measurements in this way. This is a chart showing the radius of a planet versus mass, and all these lines are lines of constant density and the different compositions that you can have. So in this case, you have pure hydrogen helium, so all gas. You go down here, you have things that are made out of water, things that are made out of rock and iron, things that are pure iron. And you can see where some of our planets sit, okay, because we're planets that are kind of between rock and iron. And here are the gas giants. Here are these are the ice giants, here are the gas giants, Jupiter and Saturn. And you can see that we have planets that span this entire range of different densities, right? All sorts of different compositions. Now, some of them are pretty weird. This stuff up here is something that's lighter than pure hydrogen helium, which, by the way, is not possible because hydrogen helium are the lightest gases. But we do see planets that appear to have densities that are so low that if you had sort of the great cosmic ocean, they'd be little bobs bouncing around in there, right? Jupiter would not. Jupiter is big enough that the gas is compressed in the inside, so you actually have a very dense interior, and the average density is actually greater than water. But we have these really light planets, and what we think is that these planets are not, like our planets where they're kind of sitting way outside from the sun and they're just sort of evolving by themselves. We think they're getting extra energy from the stars by being so close to them. And that extra energy is literally puffing them out bigger than they're supposed to be. So here we see a star-planet interaction. Again, something we don't see in our own solar system. So the density not only tells us something about the composition, it might tell us something about the evolution of these planets and how they interact with their stars. So that's cool. You can also find planets that have unusual densities and start playing around with what kind of compositions they might have. Now, keep in mind, density is one number. So there's a lot of what we call degeneracy in figuring out what the material actually is inside of a planet. Right? You can put in different materials and still get the same density out of it. So this is a little bit of sort of a game that gets played. But it is, in principle, possible to have planets that instead of made out of like rocks and iron like our planets are, all right, so something like this, they could have planets that are made, something like this, we could have planets that are made more like carbon, right? Carbon sort of composition. So you could have a carbon crust and mantle, right? Carbide is sort of a metal of carbon that could be one of the materials that you could possibly make planets out of it. Why would we care to have a carbon planet? Why would that be interesting for astrobiology?
Because all life on Earth is carbon-based.
Yeah.
Yeah.
Yeah. All of life on Earth is based on carbon, but our planet isn't, majority carbon. Our planet's majority silicon and oxygen. But if you had a planet that was made mostly of carbon, maybe there would be life all over the place. Who knows? Right? Certainly that's not something we see in our solar system, but it's something that's possible given the densities that we see. You can also have worlds that are completely covered in water, completely water entirely, right? Ice core and water on the outside, right? These are ocean worlds. Other materials could be made out of these things. These are all sort of possibilities that are beginning to open up because we can actually start measuring the densities of these planets, right? We won't really know until we actually take a spectrum of the sort of atmosphere or the surface of the planet, but these are all possibilities that are starting to be considered for these different worlds. All right, so I mentioned we can also look at as the planet goes behind the sun. That's looking at the thermal emission. That's called a secondary eclipse. So here's kind of an animation of that. If you're taking a picture of the star and planet, of course you don't see them separately because they're so close to each other, but you see the combined light. And then the planet goes behind the sun, right? You get one spectrum there, you get a spectrum just of the star. You can then subtract those and get a spectrum of the planet itself, right? This is kind of detecting the planet directly. Kind of, because we are detecting it directly here, but it's mixed up with the star. So as long as we can get a picture of just the star, we can subtract those and get a picture of the planet. Yes, sir.
Okay, so using this technique, when it goes behind, there's a dip in the spectrum.
Yeah.
Does it also dip when it goes in front?
Yes.
Okay.
Yeah. And so you have to know what part of the orbit the planet's in. I'll show a picture. It's actually pretty clear that the dips are very different because the star is very bright, so the dark spot going in front of the star has a different effect than a very, very faint bright spot going behind a bright thing. Right? So, but you can measure that, and here's some of the first measurements that were done of this about 10 years ago with the Spitzer spacecraft, and you can see that, these are error bars, and so this is a very tough measurement. But still, you're getting just a little bit of a dip in the brightness from this technique. We can monitor this across the entire orbit, and so this is getting back to your question. As it passes in front of a star, you get a big dip here. If we wait 1/2 of an orbit period, we see this little dip here, and that's the difference between the primary and secondary transits in the infrared. Because again, we're measuring the heat from the planet, and the contrast is much lower in the infrared, so this is the only way we can do this. Now, the interesting thing here is there's actually a variation that occurs even between here. And we can use that variation to actually make a map of the heat coming off the planet. So we can't take a picture of the planet, but because it's changing its orientation over time, we can kind of slowly map out what its surface looks like. And what we're finding is, in fact, the hottest part of these planets is not directly under the sun, but it's a little bit off to the side. We think that's because there are winds that are being generated from this planet that's actually pushing the heat around and actually pushing it all around the entire planet. We're actually measuring weather patterns on these planets based on the sort of brightness variation as it orbits around the star. So you can see we can start to dive into pretty specific details about these planets by making these measurements. Another interesting thing is if the planet passes in front of the star here, we've mostly talked about how it blocks the light from the sun, but some of the sunlight will come through the atmosphere, just like when we have an eclipse of the moon by the Earth, some of the light gets refracted around the Earth's atmosphere and the moon turns red, right? That's refracted light through the Earth's atmosphere. We can do the same thing on these exoplanets, right? So here's an example of Venus passing around the sun. We kind of see this little hazy stuff that's around the edge. By the way, that measurement was, when it was originally made back in sort of the 19th century, was the first time we had evidence of an atmosphere around another world, right? When rocky bodies pass in front of the sun, they're very sharp edges. When planets with atmospheres pass in front of the sun, they have these sort of fuzzy edges, right? So that's evidence that there's atmosphere. So we can do this as well for these extrasolar planets. And what we find is that how much light is blocked changes as a function of wavelength. Where you have these peaks, this is places where you have a lot more absorption because there's some atom or molecule that's in the presence of the atmosphere that's actually absorbing more and making the planet look a little bit bigger at those wavelengths. And so we can line that up with where we know certain atoms or molecules absorb, and we can actually measure how much sodium or potassium is in the atmosphere of this planet that we can't actually directly see. It's kind of amazing. So folks are looking for things like water, methane, biological molecules by using this technique of looking at the atmosphere as it passes in front of the star. Okay. All right, so in the few minutes I have left, what have we learned from all these different observations? And there's many other things that we can learn from these techniques, so we just don't have a lot of time to go through all of them. But what have we learned from them? Well, first of all, what we now know is that planets are extremely common in the galaxy. And that's a big step because, again, about 20 years ago, we didn't have any examples of planets outside our solar system. Now we're actually pretty sure that planets are a fairly common composition. So this is showing the fraction of stars in our galaxy that have at least one planet of these different types. So Earth-type planets, super-Earths, this new category, mini Neptunes, large Neptunes, or this range of ice giants, and then sort of big giants, planets like Jupiter. And this is based on, I talk about all these biases from all these different techniques. This is based on correcting for all those biases and sort of estimating how many you would have if you could actually see all of them, right? We know how those techniques actually bias our sample, so we can back out what the underlying sample is based on those corrections. And what do we see? We see that most of the planets in our galaxy are actually small terrestrial-sized planets. Even though we see a lot of these big gas giants, the techniques are kind of designed to find those gas giants. So we're kind of having a sort of a skewed view of how many there are actually out there. In fact, they're relatively rare. Something like maybe a few percent of planets in our galaxy are of these big gas giant kind. Most of them are Earths and super-Earths, all right? And I do mean most, all right? This is 20%, this is around 18%. So, getting close to like half of the planets in our galaxy are Earth-like worlds. That's pretty darn exciting, right? That means that, there may be lots of places where life could originate. What else do we know? So we talked about they span a broad range of masses. They also have a broad range of orbital properties. And importantly, they have often very different properties than the planets that we have in our solar system, right? If we used our solar system as a template for all planets in the galaxy, we'd actually get it wrong because there are all these other different types of planets that are out there. Jupiters that are very close to their suns, these super-Earths, and things that have really unusual orbits. So this is, by the way, you're going to be exploring this in your next homework assignment with a data set for this, but I'll just go over some of the highlights here. Most of the planets in our solar system are, again, very circular as they go around the sun. This is one of the patterns of the solar system that was used to infer the idea of the solar nebula, where the planets actually came from, the sort of the disk of material, and it came out as disk in circular orbits. But in fact, when we look around the solar system, or other solar systems, we find that planets have all sorts of crazy eccentricities, really high eccentricities. Remember, eccentricity is sort of the oblongness of the orbits. So these things up here are traveling around their systems just like comets, right? They're coming from very far distances and coming very close. Here's one of the coolest planets that I think exists. This is HD 80606b. It's the 80,606 star in the Henry Draper catalog. That's where the name comes from. And B is the planet. And it is a giant planet, so it has a mass that's a few times the mass of Jupiter. But instead of going around the sun in this nice little circle, it comes in from some crazy far direction and then comes in within just a few radii of the sun in which it's orbiting. Right? It's exactly like a comet, except it's a gas giant comet. And because it comes in so close, I showed you this sort of light curves of how the planet's light changes over time. Here as it's coming in, it passes in front of the star, so you see this dip, and then you see this extra light component. This is because the planet has been heated, it's literally been doubled in its temperature because it's gotten so close to its star. It's gone from about 800 Kelvin to 1500 Kelvin in a few hours. And we have no examples of this in the solar system, of taking a giant planet and suddenly making it hot. Right? Jupiter's pretty cold. So this is a completely new type of star system, but it's out there, right? It's something that we sort of now we know because we can see these things. I've talked a little bit about this, that it's this whole, all of these different properties sort of challenged our model of how solar systems form, right? This idea that giant planets have to form outside the frost line and stay there is at least partially incorrect, because now we see Jupiters that are close to the suns. So it must be that the sort of modification of this, there could be migration. Another possibility is that these planets could also just be scattering off of each other as they form early on. All right? We think our planetary system is fairly stable, but if, for example, if you've got a planetary system, we've got two planets that are close to each other initially, as they sort of pass around the sun, they can actually give themselves little kicks that eventually, here, wait for it, will give it a nasty little bump right out of the solar system, right? And what are you left with? You're left with a highly eccentric giant planet, right? So we think that some of these eccentric star systems may just be cases where these planets have scattered off of each other. And fortunately, that has not happened in our solar system, because it probably would have wiped out most of the terrestrial planets. But it's certainly something that seems to happen in other solar systems. Now, one last weirdo. Yes, sir.
So do those planets just go floating around in space, or do they join another star system? Is there big distances between?
They may go floating around in space.
Okay.
So we're now starting to find, and sorry, this is a little dark, little red spots in space. This is just an infrared image of a very faint and very low mass object that we're calling free-floating planets. These are things that are less massive than some of the planets that are found around other stars, right? This is down to less than sort of 10 or 5 Jupiter masses, which is right around the range of masses of planets that we found on other stars. But it's not orbiting a star. It's just floating around in space. So is it possible this is an ejected planet, just in the simulation we've shown, or maybe it's actually formed this way? Did you have a question, Laura?
Yeah, these planets that are like, they hit, like how does the gravity not stick them together, or is just the impact just so much that it hits the other one off? And like, are they made of the same materials? Because if it's like a gas giant and then a terrestrial, then what would happen?
Okay, so unpack a couple questions. So in principle, so when planets are forming early on, in principle, they will stick together. But when the planets are really big like this and they're moving in relatively fast orbits, the speeds at which they pass by each other so quick, and they're still small objects, that even if they pass just a little bit by each other, the gravitational tug was enough to just toss things out. So they could collide, and I showed a picture of Fomalhaut B, which has this sort of orbiting spot, and we think it's actually asteroid collisions happening there. So that happens. But it's very rare to have whole planets run into each other, just because the solar system is very big. But they can get close enough together where they literally kick each other around. And that's the kind of simulation we show there. And the other question is if they're made of different stuff.
Yeah.
That can certainly happen, and usually the winner is the gas giant planet, because of mass. They feel the same force from each other, but because it affects a different mass, the acceleration of the little planet is much higher. So it's usually the little planets that get tossed out. So this thing might get tossed out, but it would have been tossed out by something even bigger than it, most likely. So we don't know if this is something that has been tossed out. We don't know if this is just how little stars form. But these are the kind of systems that we're now finding out in the universe. So planets are a lot more complicated than they were 20 years ago. We have a lot of diversity in the types of worlds. And next week, we're going to sort of dive into, with all this diversity, what is the likelihood we're actually going to find any kind of life? Okay, so don't forget, give, if you still have some comments for our speakers, please give those. Don't forget to look at your grades and let me know if there's anything missing. And if you have needs revision comments on your project proposal, please come see me right now or in office hours. You come see me right now?
Yeah.
Okay. All right. You close up everything first.